Okay, guys, so we're going to continue on with trigonometric identities and also proofs. They're kind of related to each other. Um, let's take a look here. That. Okay, so last Zoom meeting, we talked about the following identities. So we talked about secant theta. I'm going to just call it secant x here. That's 1 over cos x. Cosecant x is equal to 1 over sine of x. Then we also talked about how, well, I guess we say cotangent of x is equal to 1 over tangent of x. But we also looked at how the tangent of x was equal to y over x, which is the sine of x over the cos of x. And of course, the cotangent, if it's 1 over tan, then we could take the reciprocal of that, and that would give us cos x over sine x. And then we also have the Pythagorean identity, sine squared x plus cos squared x equals 1. And we said there's sort of two derivations of that, which would be that the sine squared of x would equal 1 minus the cos squared of x, and the cos squared of x would equal 1 minus the sine squared of x. So this last one that I wrote, I'm going to put it on a box here. It's actually the same identity. It's just different ways of writing it. And this is what we refer to as the Pythagorean identity. And we saw how that we could use this to take what look like quite complicated statements and rearrange them. And so I'm going to just do two review questions here, just to sort of get the juices flowing on how to solve questions like this. So sine x over cosecant x plus cos x over, let's say, secant x. Okay, so right now we've got all these different trig terms. It looks, pretty ugly. You can try to work through it on your own if you want to pause the video, but I'll write a second one beside it so you can try this also. Let's try, let's try secant squared x minus 1 multiplied by cotan squared x. Okay, just try to manipulate these two. They're two separate questions. Maybe I'll put example 1, example 2. And I would really encourage you to pause the video, see if you can do it on your own, and then maybe see if you've made some mistakes where they are. Okay, so the first one, my advice in the last video was to turn everything to sine and coses if they're not already sines and coses. So this would be sine x over top of 1 over top of sine x. And now you'd be adding cos x over top of secant, which is 1 over cos. Now you do have to remember that if you take a number and you divide it by a fraction, let's say b over c, that's a divided by b over c, which is really a multiplied by c over b. So you get ac over b. So when we take this fraction, we're taking sine x dividing it by 1 over sine. That becomes sine x times sine x, which is sine squared x. And cos x divided by 1 over cos x is cos x times cos x, which is cos squared x. And that's actually the Pythagorean identity that equals 1. You can see that up above there. Okay, so so that rather ugly looking expression can be simplified to 1. It's just 1 actually. Now technically that statement we just wrote, the example number 1 there, since that's a true statement, that technically would be an identity. But we don't get you to memorize every single identity because there would be an infinite number of them. So what I would say is you should really try to remember these identities above, and they're really quite useful for most of the questions you're going to come across. Okay, so example number 2. So once again, I'm gonna default to sines and coses. Once you get better at this, like once you get more practice, you might actually do different approaches. You might say, well, that Mr. Dixon method of changing things to sines and coses isn't the best method in this choice, but it's up to you. I'm going to sort of leave that in your hands. But I think if you turn everything to sines and coses, you have less to worry about, less things to look at. You might remember in logs, we said you can always work in base 10 logs to solve problems, but sometimes it's more to your advantage to choose a different base. And the same goes here. You might have a different method that gets you to the same answer and takes fewer steps, and that's totally fine. Okay, so but I'm going to still stick to the convert to sine and cos method here. So secant is 1 over cos. So secant squared would be 1 over cos squared x, and I'm minusing 1, and I'm timesing that by cotan squared x. Remember, cotan squared x is cos over sine. So this would be multiplied by cos squared x over sine squared x. That is cotan x. Now, I deliberately left the 1 out, and just to save space here, what I notice, I have 2 terms in the brackets here. So I've got the 1 over cos squared x minus 1, and I'm going to try to turn that into one term. That was our second rule we tried to follow. So first thing is turn things to sine and cos, and then the second thing is to combine terms if you can. So I need a common denominator here, so I'm going to turn this into cos squared x over cos squared x. That's the same thing as 1, okay? So now on top I have 1 minus the cos squared of x all over the cos squared of x, then brackets, multiplied by cos squared of x times the sine squared of x. And you might be able to sort of see what's about to happen here. But once again, it's kind of new, so maybe you're not seeing it right now. Now, if I look at example number 1, I used the Pythagorean identity at this stage to get to 1. If you notice, we actually have the Pythagorean identity in the first fraction. We notice we have 1 minus cos squared of x. So that equals sine squared of x over cos squared of x. And I'm timesing that by cos squared of x over sine squared of x. So these are going to cancel for us. So cos squared x, sine squared x, and we get 1. Now, I just chose those 2 questions at random, so I don't want you to get the sense that they always equal 1. They don't always equal 1, but this is just fortuitous, I guess, that happened. Okay, so let's talk about proofs now. How do we, what is a proof, first of all? So proofs are a way in math that we can verify that one side of the equation is the same as the other side of the equation. And it is important to understand that proofs are a little bit different. They're a little bit different than an equation. There's certain rules you can use during a proof that you I should probably rephrase it. There's certain things you would do when you solve an equation that you can't actually do when you're solving a proof. And one of the things is you can't move stuff from one side of the equation to the other. So all you can do is not move things. So, so let's take a look at an example here. So let's say you had cos, so it's going to look similar, cos squared theta, sorry, cosecant squared theta minus 1 over top of cosecant squared x, and we say that that equals cos squared x. So we're saying that the left side and the right side are the same, but we ask you to prove that, like prove that that is true. And so that's a sort of a tricky question. And so the only way you can prove it is using rules that already exist. And what you are trying to work with are the identities. So the identities that we've given you so far, that's really all you need to know to answer this question. But let's go through it and see what we get here for this. Okay. So there's many ways to do proofs. So I don't want to like lock you into one method. But what I would recommend you do first for proofs is to pick a side. And I mean, what I mean by that is pick a side to work with. So either the left side, I'll call that LS, or the right side. And generally what you'll see is when I give you your test or quiz question, I'll put a line down the middle. Go down, put a line down the middle. And basically at the very end, the left side should equal the right side. It should look exactly the same. So what I'm trying to do is take the left side and make it look like cos squared x, or take the right side and make it look like cosecant squared x minus 1 all over cosecant squared x. And at university, that's kind of what you have to do if you're going into these kind of courses. You can only work with one side. But in Math 12, we kind of allow you to work with both sides if you want to. As long as one side now looks like the other side, you could stop. That means you've proved the proof. So the first thing I do is pick a side. So I always choose the side that seems to have more stuff on it, more things that I could work with. So to me, the left side has a lot more things I can manipulate, whereas the right side is just this cos squared x here. So I'm going to try to prove that the left side is the same thing as the right side. And so once again, I might go default here to changing things to sines and coses. So the left side, I've got 1 over sine squared x minus 1. I'm going to leave the 1 out for now because I'm going to do that change I did before. And that's 1 over sine squared of x. Okay, and right now it's actually not looking great because notice the right side is cos squared of x. So I'm hoping something's going to pop out here that I can work with. So number 3 was to combine terms. So very similar to what we did on the Zoom meeting. Okay, so I'm going to bring this 1 together. So the 1 that I have right here. So I need to turn that into a fraction that has sine squared on the bottom. And so I'll have sine squared on top. So now what I have is I have 1 minus sine squared x all over sine squared x. Now I'm dividing by a fraction, which is the same thing as multiplying by the reciprocal. I'll do that. You can already see some canceling going on here. And now I've got this 1 minus sine squared x, and I can sort of see the sine squared x's are going to cancel. But what is 1 minus sine squared x? Well, that is the Pythagorean identity. 1 minus sine squared x is the identity cos squared x. And that's good. So you've got cos squared x over sine squared x multiplied by sine squared x. So the sine squared x's are going to cancel. And I'm going to be left with cos squared x. So now my left side is exactly the same as the right side. Now, I'm just going to show you maybe a different technique here. Sorry, just before I finish that, so combine like terms, and then the other option, of course, is to number 4, look for identities. So by identities, I mean the Pythagorean identity that we saw here, being able to turn that into cos squared. Sometimes you have to look for those things, not as obvious as you might think. Okay, so let's actually, I'll come back to this question a bit later and show you a different way of tackling it. But that's one way to approach it. It's basically the starting stages of doing proofs, and once again, look for sines and coses. That's usually the easier way to do that. Okay. So let's take a look at where are we here? Oh yeah, sorry. Actually, no. Sorry. I'm jumping all over the place. Instead of coming back, that would be ridiculous. Let's not come back to that. Let's take this part. And what I'm going to do is I'm going to go over here, pretend like I hadn't done what I just did here. And just to show you there's alternate ways of doing this. So I could write this as cosecant squared x over cosecant squared x minus 1 over cosecant squared x. Okay, so I'm just splitting it into 2 fractions now, which is kind of the opposite of combining terms, by the way. So that's why I didn't want to do it that way at the beginning, because I was making a big thing last day about try to combine your terms. So here I am actually making 2 different terms. But the reason that this is a bit nicer is that cosecant squared x over cosecant squared x is 1. And then 1 over cosecant squared x is sine squared x. So you have 1 minus sine squared x. And of course, that's still the Pythagorean identity, cos squared x. Okay, so you can see that this alternate way of doing it has fewer steps to it, but it's not any better or worse than what we did before. It's just a different way of doing it. And so you could actually, for many of these questions, have like 7 different ways to do them. But what I mark you on is each step. So one of the things you really got to be careful of is you have to show me every single step you did. So if you just kind of did some voodoo math in your head and got down to this answer without showing me that, then you would lose marks for that. So every step must be shown to show your logic and how you got to that answer. So it is a bit tedious to do a proof. You got to kind of show all the steps to it. Okay, so let's take a look at a different question. Let's try, that looks kind of fun. Let's try proving let's prove that tan x plus cotan x is equal to secant x multiplied by cosecant x. So we're saying that the left side, the tan and the cos, when you the tan and the cotan, when you add them, they give you the same result as secant multiplied by cosecant. So what I would do here is let's divide the column approach here. Is I would pick a side to work with. Now both sides have quite a bit of stuff you can work with here. I kind of am leaning to the left side because I've got this addition sign here. So I'm thinking I can at least bring those terms together at some point. But you know, once again, you should be able to reach it from both sides. So it's a bit of practice. You'll get kind of a feel for it, and then go from there. So I'm going to work just with the left side right now. So I'm going to say tan is sine x over cos x. Adding to that cos x over sine x. Okay, so now I've converted everything to sine and cos on that side. And technically I could do that to the right side, but let's just keep it as it is. Now, in order to add two fractions together, you have to have a common denominator. So my LCD here seems to be sine x cos x. So I'll times the bottom of this by sine x. I do want you to show me that. That's what you did. And times this by cos x. So now I have an LCD that is sine x cos x. And the numerator would be sine squared x plus cos squared x. And once again, there's that Pythagorean identity. So sine squared x plus cos squared x is 1 over sine x cos x. Now, there's two ways that I think students would go on this one. One is they would keep going with the left side, and they would say, well, I know 1 over sine is cosecant, and I know 1 over cos is secant. So really, this is secant x multiplied by cosecant x. And now you would be complete here. But some students might choose, and you can do this, is also with the right side when they change things. They could have said, well, this is 1 over cos x times 1 over sine x, which of course is 1 over cos x sine x. And they might have stopped here, but then you wouldn't have done this part. That wouldn't make sense. You would have stopped here because you want to stop as soon as the two sides are saying exactly the same thing. Okay, so you want to make sure that you follow that pattern there. Okay, so so there's one there. Let's try one more that involves sort of a fancy little trick that we have to deal with here. So this is our last one for the day. So prove that we're over here. Cosecant x plus cotan x, cosecant x plus cotangent x. Prove that that is equal to sine x over 1 minus cos x. Okay, so we got this statement that has a left side that's got some cosecants and cotangents, and a right side that actually has sines and coses already. And so once again, I would pick a side. I would choose a side. Now, the right side does look a little more fancy because it's got a fraction and something or other. But really, I've got sines and coses already, so I'm kind of leaning to the left side again. So I'm going to change the cosecant and the cotan into sines and coses. So cosecant is 1 over sine of x plus cotangent, which is cos x over sine x. And I'm trying to combine terms, so that's really quite good right now. I've got the same denominator in both. So I'll say this is 1 plus the cos of x all over the sine of x. And now if I look at these two things, they're really close. I mean, they got sines and coses, but they seem to be kind of like flipped, and then there's like a plus sign in one and a negative sign in the other. So really at this point, if you follow the rules I've given you, it would seem like this is all you can kind of do at this point here. So all you've done. So what I'm going to encourage you to do here, if you get to this kind of statement and you're not sure where to go from this, we're going to use the force. Okay, so we're going to force something here. And what I'm going to do is I'm going to force an identity to appear. So I'm going to force an identity to appear that's not here right now. But before I do that, I want to just go over a little review thing. Back in grade 11, you've learned this, and we've talked a lot about this in grade 12 math. If you have a plus b and you multiply it by its conjugate, a minus b, you wind up creating a difference of squares. So this gives you a squared minus b squared. And this is the technique we're going to employ for this kind of question, okay? And that is we're going to force an identity to appear by multiplying by the conjugate. So we're going to take a look here and see if we can find some conjugates here. Now, if you want to keep working with the left side, you can do that, but you could also switch to the right side. So I'm going to show you both ways here. So what I'm going to do to the left side, just keep working here, is I'm going to notice that on the right side, I've got this 1 minus cos x down there. And I need that to be there on the right side, or on the left side, to be the same. So I'm just going to stick it down here. Go 1 minus cos x. So there it is. That's exactly the same as the other side, except I've got a sign I got to get rid of. And I got to get rid of this 1 plus cos x. And the other problem is, of course, you can't just times a fraction, the denominator of a fraction by a number and not do something to the numerator, otherwise it won't be equal. So I'm going to times top and bottom by the conjugate. Okay. So right now on the bottom, I'm going to have a sine x. I'm not going to distribute. I'll show you why here. You're going to have 1 minus cos x, because you want that. You want to be able to see the 1 minus cos x so you know you're going in the right direction. But what does the top equal if you do that? So you got this binomial times that binomial. So if you FOIL that out, first, outer, inner, last, well, you're going to get a difference of squares pattern, which is going to be 1 minus cos squared of x. And 1 minus cos squared of x is sine squared of x. So once again, you have to show all these steps. Sine of x, 1 minus cos of x. And now I can get rid of one of the sine x's here. And so you get sine x all over 1 minus cos x. So it's a pretty neat little trick you can do using the conjugates. But I want to show you with the right side how we could have done the same thing. And so once again, I'm going to show you how we can get to the purple answer here. So remember, we got to that purple answer. So imagine that's where you stopped. Okay, you stop there, and you didn't do all the stuff in red, okay? So what I'm going to do is I'm going to say, well, what do I want on the right side? Well, the purple thing has this 1 plus cos x in the numerator, so I'm going to times the top by 1 plus cos x. There it is. I've just made it appear, okay? But whatever I do to the top of the fraction, I have to also do to the bottom of the fraction. So that would give me sine x multiplied by 1 plus cos x all over. Now when I FOIL this out, or do my distribution, I get another difference of squares pattern. I'm multiplying two conjugates. So 1 minus cos squared of x. So I get sine of x times 1 plus cos of x all over sine squared x. And then signs cancel. So I get 1 plus cos of x all over sine of x. And that equals the thing in purple there. Now, really important, I'm hoping you're listening very closely here, you don't do both these things I've done. You just do one of them, okay? Because what you're trying to do is make one side look like the other side. So if I was to stop right now, I actually did this, I wrote everything out here, you're saying this is the same thing as that, and that is not the same thing. It looks different to me, okay? So once again, you want to stop as soon as you get both sides looking the same, okay? So I'm just trying to show you in how you could have got sides. Okay, so you should stop. Stop. So today's lesson was on proofs and identities and how to work with. So hope you're doing well. Have a great weekend, and we'll talk to you later.